look at this world, a peaceful sanctuary of blue and white drifting silently in the void. But to see the truth, we must strip away the oceans, the life, and the peace. We return to the beginning, when our home was nothing but a burning sphere of molten rock. The sky was a weapon, raining down cosmic debris that pulverized the fragile crust relentlessly. Then a shadow appeared in the darkness, a wandering world on a collision course with destiny. The impact was absolute, a cataclysm so violent it nearly erased Earth from existence. Yet from destruction came creation. The debris settled, the fire faded, and the planet began to heal. Temperatures dropped, and thick clouds gathered, choking the sky, waiting to unleash a new force. Then a miracle occurred. The first drop of rain fell, marking the beginning of the Great Deluge. From a ball of fire to a world of water, this is our genesis. Welcome to Cosmicorigins. 4.5 billion years ago, Earth was an entirely alien world, unrecognizable, unfinished, and utterly different from the planet we know today. There was no sky above, no oceans below, and no solid land capable of supporting even the most primitive forms of life. The infant planet existed as raw matter and violent motion, driven by extreme heat and uncontrolled planetary energy. Below us, the surface burns relentlessly, glowing across vast horizons beneath an atmosphere saturated with crushing heat. A global ocean of molten rock blankets the planet, endlessly churning and shifting without pause, balance, or stability. Rivers of lava tear through fractured crust, carving glowing scars and constantly reshaping Earth's unstable surface. The atmosphere is thick with carbon dioxide, sulfur, and towering clouds of superheated steam. Violent lightning erupts through dark skies, born from intense heat, pressure, and extreme atmospheric instability. Yet planetary violence continues as the early solar system remains chaotic, unstable, and filled with wandering debris. Countless asteroids and comets drift inward, drawn by gravity toward the vulnerable surface of young Earth. They strike at unimaginable speeds, tearing through atmosphere and molten ground with devastating force. Each impact releases staggering energy, instantly rewriting vast regions of the planet's surface. Solid rock vaporizes on contact, transforming instantly into expanding clouds of superheated material. Fire spreads outward from each collision, repeatedly resetting Earth's surface again and again. Yet these impacts are not only destructive, they also deliver essential materials from deep space. Metals, rare minerals, and ancient water arrive hidden within icy and rocky cosmic debris. Through constant destruction, Earth quietly gathers the ingredients it will need for a distant future. Over millions of years, intense internal heat slowly escapes the planet into the cold vacuum of space. The global magma ocean begins to cool, gradually losing energy after countless violent ages. Dark plates of solid crust finally form, floating like rafts atop glowing molten depths. Volcanoes dominate the landscape, endlessly releasing fire, gas, and molten rock from below. The atmosphere thickens further, trapping heat and creating a powerful, long-lasting greenhouse effect. Earth remains hostile and extreme, yet subtle changes signaled the first approach toward stability. By 4 billion years ago, the planet's crust becomes increasingly permanent, stronger, and more resilient. Minerals condense and fall from the dense sky, settling across the slowly cooling surface. Jagged landmasses rise from below, barren, lifeless, and newly exposed to the toxic air. Some of these ancient rocks will survive for billions of years into Earth's distant future, They remain today, silent witnesses to the planet's earliest and most violent memories. The environment is still deadly, filled with toxic air and extreme surface temperatures. Volcanic fire continues shaping the horizon, though chaos slowly begins to fade. Seen from space, Earth glows like a wounded ember suspended in endless darkness. The planet was scorching hot, a global desert of basalt and fire. But help was coming from the edge of the solar system. It arrived not as a gentle rain, but as a bombardment. Millions of icy comets and asteroids smashing into the surface, delivering the most precious cargo in the universe.
Asteroids and comets are pulled inward, heating violently as they plunge toward Earth's thick atmosphere. These objects strike the surface with unimaginable force, detonating energy beyond anything seen today. Each impact releases blinding heat, instantly rewriting the landscape beneath expanding shock waves. Solid rock vaporizes on contact, flashing into clouds of superheated gas and molten ejecta. Fire spreads across the planet, repeatedly resetting Earth's surface through relentless bombardment. Yet these impacts bring more than destruction. They deliver essential materials from deep space. Metals, rare minerals, and crucially, water locked inside ancient ice arrive with each collision. These elements sink into molten layers, chemically enriching Earth from within over immense timescales. Slowly, Earth begins to cool, radiating its internal heat outward into the cold darkness of space. The magma ocean loses intensity, convection slows, and darker regions begin appearing across the surface. For the first time, solid crust forms, dark plates floating like rafts atop molten depths below. Volcanoes erupt constantly, releasing vast amounts of water-rich steam and volcanic gases into the sky. A dense steam atmosphere develops, trapping heat and storing enormous quantities of water vapor. As temperatures drop further, surface motion slows, and conditions approach the stability needed for liquid water. A continuous crust forms, strong enough to retain water without immediately boiling it away. Steam begins to condense, forming mist, droplets, and finally, the first rainfall in Earth's history. Liquid water flows across hot rock, collecting in low basins and carving primitive channels. Evaporation and rainfall repeat endlessly, establishing Earth's first primitive water cycle. For millions of years, rain falls continuously, filling basins and slowly raising global water levels. Oceans spread across the surface beneath a still toxic atmosphere, transforming Earth into a water-dominated world. Volcanic activity diminishes, storms stabilize, and planetary systems gradually approach balance.
Earth now had water. It was cooling down. It was almost peaceful. But the solar system was still a violent shooting gallery. Another planet, a wanderer named Theia, was on a collision course. This wouldn't just be an impact, it would be an execution. The day Earth nearly died, and the Moon was born. Earth emerged from violent collisions, growing through chaos, gravity, and unimaginable planetary energy forces everywhere. Early Earth's surface was a global magma ocean, constantly reshaped by impacts and internal heat. Meanwhile, a colossal impact reshaped Earth, ejecting debris that would eventually form the Moon itself. Molten debris orbited Earth, forming a thick, chaotic disk of rock and vapor around equator. Within this debris disk, gravity slowly assembled the Moon from Earth's own material over time. The Moon stabilized Earth's tilt, moderating climate and protecting long-term environmental balance for future eras. With stability achieved, oceans persisted, surviving impacts and gradual atmospheric evolution across deep geologic time. The dust settled. The debris formed our moon. But on Earth, the heat from the impact lingered. It took millions of years for the magma to harden into a crust, and then the skies opened up. The longest rainstorm in history began to fill the basins of the world.
For millions of years, Earth burned. Not dramatically, not explosively, but relentlessly. There was no single catastrophe to mark this era, no defining moment, only persistence. Heat radiated outward, escaping the planet grain by grain, photon by photon, into the endless cold of space. This was not change by force, it was change by time. And time in the universe is patient. Slowly, almost imperceptibly, the planet began to lose its glow. Seen from orbit, Earth transformed. Its blinding brilliance faded. Dark patches appeared on the surface, like scars forming on cooling skin. These patches cracked, drifted, shattered. They were the first crusts, fragile skins floating atop a sea of fire, ephemeral, temporary, yet they represented something profoundly new. For the first time, Earth was learning to let go of heat. Cooling had begun. Below these unstable crusts, the planet remained furious. Volcanoes dominated every horizon, erupting continuously, spewing steam, carbon dioxide, sulfur compounds, and ash into the sky. Each eruption reshaped the surface. Each eruption reminded the universe this was still a world hostile to existence. But the atmosphere was changing. Water vapor accumulated, layer upon layer, growing heavier, growing thicker. Immense clouds began to form, towering beyond anything seen on Earth today. They wrapped the planet completely, hiding the surface in perpetual darkness. Within these clouds, energy gathered, pressure mounted, until equilibrium could no longer be maintained. Lightning ripped across the sky, not as isolated flashes, but as constant planet-wide storms. And then, rain. Not gentle rain, not nourishing rain, but rain as violence. Water crashed down on incandescent rock, boiling instantly on contact, exploding back into vapor. Again and again and again. Rain fell, water vanished, vapor rose, clouds thickened, and rain returned. A planetary cycle without rest. This went on not for days, not for centuries, but for hundreds of thousands of years. The Earth endured, and slowly, almost quietly, the surface temperature dropped, until one moment, not dramatic, not announced, everything changed. For the first time in Earth's history, water touched the surface and did not disappear. It stayed. That moment passed unnoticed by the universe, but it altered everything. Water pooled in the lowest places. It seeped into fractures in the crust. It gathered in vast depressions left by impacts and tectonic violence. Basins deepened, darkened, and under an orange, mineral-rich sky, they began to reflect light. The first oceans were born. They were nothing like the oceans we know. They were not blue, they were not clear, they were not calm. They were warm, murky, saturated with dissolved minerals. Their waters churned constantly, stirred by tides, heated from below by magma, and battered from above by falling debris from space. Yet these oceans did something extraordinary. They changed the destiny of the planet. Water absorbed heat that rock could not. It drew carbon dioxide from the atmosphere, locking it away in solution in stone. It redistributed energy across the globe, smoothing extremes, dampening chaos. Earth began to settle. Above, the moon, closer than it is today, pulled relentlessly at the young seas. Tides surged across the planet, mixing water, minerals, and energy on a global scale. For the first time, Earth had a rhythm of rise and fall, a rhythm of circulation, a rhythm of balance.
We have land, we have oceans, but if you were to stand on those ancient shores and take a deep breath, you would die instantly. This was not the air we breathe today. This was a heavy, suffocating blanket of volcanic exhaust.
This world is violent, unforgiving, restless. And with every eruption, Earth exhales, not metaphorically, physically. From deep inside the planet, gases long locked away are forced upward, bursting into the sky above. Carbon dioxide pours out in vast quantities. Water vapor follows, superheated and dense. Nitrogen spreads through the growing envelope. Methane and sulfur-rich gases darken the heavens. This is Earth's first atmosphere. It does not arrive from space. It is not delivered by comets or asteroids drifting in from the outer solar system. This sky is born from Earth itself. There is no oxygen here, none at all. Not a single molecule capable of sustaining life as we know it today. No breath could be drawn, no flame could burn. From orbit, Earth appears wrapped in a thick, swirling haze, amber, brown, and opaque. Sunlight strikes the upper layers, but struggles to reach the surface. Heat becomes trapped below, unable to escape. This atmosphere presses down like a weight, sealing warmth inside, turning the planet into a vast planetary furnace. This sky does not protect life, it challenges it. We descend deeper into the ancient atmosphere itself. Visibility collapses almost immediately. Light scatters, fading into a murky half-darkness. Above us, clouds churn endlessly, acidic, heavy, and unstable. Ash drifts through the air, falling continuously like black snow. The sky is never clear, the horizon never calm. Rain begins to fall, but this rain is nothing like the rain we know today. These downpours are saturated with chemicals, warmed by the heat rising from below. When they strike fresh volcanic rock, they hiss violently, releasing steam and reshaping minerals at the atomic level. Each storm alters the surface, each impact changes the chemistry of the planet. To modern life, this world would be instantly lethal. A single breath would destroy lung tissue. Blood would fail to carry oxygen. Survival would end almost immediately. And yet, this hostile atmosphere is performing a role far more important than comfort. It shields the surface from intense solar radiation, radiation powerful enough to tear apart fragile chemical bonds before complexity can ever arise. It prevents Earth's heat from bleeding away into the cold vacuum of space. Without this suffocating sky, the planet would freeze. Without this toxic shroud, chemistry would fail. This is not air. It is a furnace and a shield. Time begins to stretch. Not days, not centuries. Millions of years pass. Volcanoes continue to feed the atmosphere, replenishing its gases again and again. The sky remains thick, heavy, and poisonous. But slowly, almost invisibly, change begins. Water vapor rising into the atmosphere starts to cool. Clouds grow denser, heavier. Rain becomes more frequent, more persistent. And then, something extraordinary happens. It does not stop raining. For thousands of years, for millions. Water gathers in low basins across the planet. Pools deepen, they connect. The first oceans begin to form. As liquid water spreads across Earth's surface, carbon dioxide is drawn out of the atmosphere, dissolving into the growing seas. The runaway greenhouse effect weakens. Steam thins, the sky lightens. Storms still rage, but their violence slowly diminishes. Sunlight reaches the surface more consistently. Temperatures begin to stabilize. The atmosphere remains toxic. Oxygen is still absent, but Earth is no longer trapped in pure chaos. It is beginning to regulate itself. This early atmosphere becomes the planet's silent guardian. It stabilizes global temperatures. It allows liquid water to persist over vast spans of time. It protects fragile chemical processes from the destructive forces of space. Lightning fractures the heavy sky again and again, injecting enormous energy into warm, mineral-rich oceans below. Within these waters, molecules collide. They bond, they break apart, and bond again. Chemical reactions accelerate. Complex pathways emerge. Processes that could never occur in the vacuum of space become possible beneath this dense sky and within these stable oceans. Under conditions that seem hostile, possibility quietly takes hold. By 4 billion years ago, Earth has oceans vast enough to shape climate. It has continents forming and eroding. It has a steady rhythm of day and night. The air is still unbreathable, the sky still hostile, but the stage is set. Earth waits, balanced on a quiet edge. Nothing dramatic happens in a single moment. No sudden miracle transforms the sky. Instead, Earth waits. Day after day, the sun rises over a world that cannot yet breathe. Its light filters through a heavy atmosphere, diffused and muted, painting the surface in dim copper tones. Days become years, years become ages. The oceans continue to deepen, absorbing gases from the sky above. Minerals dissolve into the water, enriching it with chemical potential.
The surface was a radiation trap. The air was poison. But deep down, in the crushing darkness of the ocean floor, something was brewing. Cracks in the Earth's crust were leaking heat and minerals. Nature was building its first laboratory.
Tonight, we descend into that hidden world, a realm of heat, of chemistry, of possibility. We sink beneath the surface of the primordial ocean. Above us, storms, volcanoes, chaos. Below us, silence. Light fades quickly. Blue dissolves into black. The water grows colder, heavier, denser. With every meter downward, pressure builds. Miles beneath the surface, the sun no longer exists. There is no day, no night, only darkness. And then, from the blackness, something emerges. Towering structures rise from the seafloor, mineral chimneys, jagged, ancient, hydrothermal vents. Built not by life, but by the planet itself. Seawater seeps deep into fractured rock, heated by molten stone, enriched with hydrogen, methane, iron, and sulfur. Then it erupts back into the ocean, violently, relentlessly. This energy does not come from the sun. It comes from Earth's interior, a remnant of the planet's violent birth. Here, the seafloor is not dead. It moves, it circulates, it transforms. Around these vents, extremes collide. Superheated water meets freezing ocean. Alkaline fluids crash into acidic seas. Hot meets cold. Order meets chaos. Minerals dissolve, then crystallize, again and again and again. Black and white plumes billow outward like underwater storms. Stone grows, fractures, collapses, then grows again. This is not destruction, it is construction, a planetary engine of chemistry running continuously for millions of years. Within the porous walls of these chimneys, tiny chambers form. microscopic cavities sheltered from the vast ocean outside. Inside them, molecules are trapped, concentrated, forced to interact, again and again and again. Carbon binds with hydrogen, nitrogen enters the mix, sulfur reshapes reactions, heat accelerates chemistry, pressure stabilizes it. Minerals guide reactions along specific paths. In this environment, chemistry is no longer random. It becomes organized, directed, persistent. Slowly, almost imperceptibly, complex molecules begin to appear. Amino acids form, simple lipids assemble, carbon chains grow longer, more intricate. There are no cells yet, no DNA, no metabolism as we know it, but something crucial has begun. A system that feeds on energy and uses it to build complexity. When one reaction ends, another begins. When one molecule breaks, another replaces it. This chemistry does not fade away. It continues. Time passes. Thousands of years, then millions. Within the vent walls, chemistry experiments endlessly. Most reactions fail, most systems collapse, but some persist. Some molecules begin to replicate, imperfectly, with variation. Errors appear, differences accumulate. Some combinations last longer, some reactions prove more stable. Selection begins. Not biological selection, chemical selection. What persists remains. What does not disappears. Gradually, boundaries form. Simple membranes wrap around clusters of reactions. Inside, chemistry continues. Outside, the ocean presses in. Energy flows across these boundaries, driven by chemical gradients, differences in temperature, in acidity, in charge. These are not yet cells, but they are no longer just chemistry. They are protocells, systems with an inside and an outside, with structure, with continuity, a bridge between non-life and life. Crucially, none of this depends on sunlight. These early systems draw energy from chemical reactions alone, a process known as chemosynthesis. Even today, modern hydrothermal vents support entire ecosystems built on the same principle. Life thriving in absolute darkness, living echoes of Earth's earliest past. And yet, for most of its existence, life on Earth has lived like this, hidden, microscopic, invisible. For nearly 3 billion years after its origin, the planet was ruled not by animals or plants, but by single cells, descendants of those first chemical systems born in darkness. They shaped the atmosphere, they altered the oceans, they changed the chemistry of the entire world, all without sunlight, all without awareness. Life learned how to survive long before it learned how to see. The ocean floor offered something rare: stability, shielded from meteor impacts, protected from ultraviolet radiation, insulated from surface chaos. Here, chemistry had time to repeat, time to fail, time to improve. Chemical gradients acted like engines. Protons flowed from high concentration to low. Electrons moved from donor to acceptor. Energy was released, not as fire, but as opportunity. This was metabolism in its most primitive form. Even today, your own cells generate energy using proton gradients across membranes. The same principle, the same physics, a continuity stretching back over 4 billion years. As protocells grew more complex, their chemistry began to specialize. Certain reactions stabilized, certain pathways became favored. information began to matter, not as language, but as structure. Molecules that preserved successful reactions were more likely to persist. Patterns emerged. Chemical memory formed. The past began to shape the future. At some point, molecules capable of storing information gained an advantage. Chains that could be copied, sequences that could be inherited, the precursors to RNA. A quiet revolution. Because once information could be passed on, evolution truly began. Not yet biological evolution, but something close. A universe that remembered what worked before. Still, this process was fragile. Most experiments failed. Most systems collapsed. Life was not inevitable everywhere. But somewhere, in one vent, in one chamber, conditions aligned just long enough. Stability met energy, containment met chemistry, and a system crossed a threshold it could not return from. From that moment on, the planet was no longer sterile. Life existed, even if only as chemistry that refused to stop. Over time, these systems spread, carried by currents, sheltered in cracks and pores. Some remained deep, others ventured upward. Eventually, sunlight entered the story, not as the beginning, but as an addition. This changes how we understand life itself. Life does not require sunlight. It does not require oxygen. It does not require calm. It requires energy gradients, chemistry, and time. That is all. And if life could emerge here, in darkness, under pressure, without air, then how rare can life truly be? Across the universe, water is common. Heat is common. Chemical gradients are everywhere. On icy moons beneath frozen crusts, on ocean worlds orbiting distant stars. The conditions that gave rise to life on Earth may not be unique at all. Perhaps the universe is not silent. Perhaps it is simply young, or distant, or speaking in forms we have yet to recognize.
The energy was there. The ingredients were there. Now, the universe began to play with Legos. Carbon, hydrogen, nitrogen, oxygen. They started to bond in ways that had never happened before. Simple chemistry was becoming complex. Before history, before memory, before the first breath was ever drawn, there was only the silence of the unfinished. Imagine a time when the concept of life did not exist. The universe was vast, cold, and indifferent. Stars lived and died in the crushing dark, forging elements in their nuclear hearts, scattering dust across the cosmos. But in one obscure corner of a spiral galaxy, gravity began to pull that dust together. It was not a gentle process. It was violent. It was catastrophic. It was the birth of our home. But the Earth you know, the blue marble, the white clouds, the green forests, is nowhere to be found. Travel back 4.5 billion years. We're descending into the Hadean Eon, named after Hades, the underworld, and rightly so. Look at the surface. There is no solid ground, only a churning ocean of magma. The heat is unimaginable. The planet is spinning wildly, much faster than it does today. Days are short. The sky is a bruising shade of orange and black, choked with thick clouds of volcanic ash. There is no oxygen to breathe. If you were to stand here, your lungs would fill with nitrogen, carbon dioxide, methane, and ammonia. It is a toxic cauldron, a world that seems determined to prevent anything from living. And yet, look closer. Beneath the violence, the stage is being set. The Earth is cooling. A crust begins to form, black jagged rock floating on the mantle. And then the great deluge begins. As the temperature drops, the steam in the atmosphere condenses. Rain falls, not the gentle rain of a spring day, but a boiling, acidic torrent that lasts for millions of years. It fills the lowlands, it drowns the craters. The first global ocean is born. It is dark, it is hot, it is rich in dissolved minerals. It is a primordial soup. And in this soup, the laws of physics are about to give birth to the laws of chemistry. The ingredients are here, simple molecules: carbon, hydrogen, nitrogen, oxygen. Let us pause to consider the architect of life, carbon. Why carbon? Because it is the friendliest atom in the universe. It loves to bond. It can hold hands with 4 other atoms at once, creating long chains, rings, and complex scaffolds. Without this unique flexibility, the story of life would end before it began. These atoms drift aimlessly in the water and the air. On their own, they are lifeless gas and dust. They need a catalyst. They need power. The early Earth is a planet of boundless energy. Look up. The sun is younger, fainter, but it bombards the planet with harsh ultraviolet radiation, unfiltered by any ozone layer. Volcanoes erupt underwater, spewing heat and chemicals from the planet's core. And then there is the lightning. Storms rage across the planet with an intensity we cannot fathom. Bolts of electricity tear through the methane-rich sky. The heat of the lightning channel reaches 30,000 degrees Kelvin, hotter than the surface of the sun. In that split second of terrifying heat, something fundamental changes. The shock wave shatters the strong bonds of the gas molecules. Atoms are ripped apart. They are chaotic, free, and desperate to recombine. Carbon grabs onto nitrogen, hydrogen latches onto oxygen. They forge new alliances, stronger alliances. Formaldehyde, hydrogen cyanide. These are poisonous to us now, but back then they were the intermediate steps, the stepping stones. As these new molecules rain down into the ocean, they react again, and slowly, from the chaos of the storm, a specific structure emerges. A central carbon atom, an amino group, a carboxyl group, and a side chain that defines its character, the amino acid. But the storm-lashed surface is not the only candidate for life's cradle. We must look deeper, dive beneath the waves, down into the crushing pressure of the abyss where the sunlight never reaches. Here we find the hydrothermal vents, not the violent black smokers that spew acid, but the gentler white smokers, the alkaline vents. These are towering cities of carbonate rock rising from the seafloor like Gothic cathedrals. Inside these rocky towers, warm alkaline water from the Earth's crust meets the cool acidic ocean water. This clash creates a natural battery, a flow of energy. The rock itself is porous, filled with billions of tiny microscopic chambers. In these tiny pockets, molecules are trapped and concentrated. Heat and minerals act as catalysts. Here, protected from the ultraviolet radiation above, simple chemicals are coaxed into joining together. It is possible that the first amino acids were not forged in the sky, but cooked in the warmth of the Earth's deep crust.
However, the Earth was not working alone. While the storms raged below and the vents churned in the deep, the heavens were delivering their own cargo. We must remember that the Earth is not a closed system. Between 4.1 and 3.8 billion years ago, the solar system was undergoing a violent reorganization, the Late Heavy Bombardment. Giant rocks, icy comets, and asteroids were flung from the outer solar system toward the inner planets. They slammed into the young Earth, pulverizing the crust. Destruction? Yes, but also delivery. We have analyzed meteorites that fall to Earth today, like the Murchison meteorite, and inside these rocks from deep space, we find something startling: amino acids. Glycine, alanine, glutamic acid. They were formed in the cold vacuum of space on grains of interstellar dust billions of years ago. Think of the implication. The building blocks of life are not unique to Earth. They are everywhere. The universe is saturated with the potential for biology. These cosmic seeds rode the backs of comets, survived the fiery entry through the atmosphere, and seeded the early oceans. So the broth thickened, from the lightning above, the vents below, and the stardust beyond. The oceans became a vast, global laboratory. But we have a problem, a scientific paradox. Amino acids floating in an ocean are just floating. Water is essential for life, yes, but water is also destructive. It tends to break down complex chains, not build them. If you leave a protein in water long enough, it dissolves back into amino acids. So how did life take the next step? How did these single bricks join together to form a wall? We need a mechanism to forge the bond, to stitch them together. We need a shoreline. Picture a volcanic island rising from the sea. At the edge of the water there are tide pools. The moon, much closer to Earth than it is today, pulls the tides with ferocious power. The water rushes in, bringing the amino acids. The water rushes out, leaving a shallow puddle. The sun beats down. The heat from the volcanic rock rises. The puddle evaporates. This is crucial. As the water disappears, the molecules are forced together, crowded into a tight space. They adhere to the surface of clays and minerals. These minerals act as a template, a scaffold. They align the molecules in the perfect orientation. As the heat bakes the mud, a chemical reaction happens, condensation. The amino acids link up. They hold hands. They form peptides. Then the tide returns. The water dissolves them again. But some of the chains hold. Day after day, million years after million years, the wet-dry cycle, the heartbeat of the chemistry. Pump, bake, link. Pump, bake, link. Nature is knitting. And here lies one of the deepest mysteries of all, the mystery of the left hand. In a chemistry lab, when you create amino acids, you get an equal mixture of left-handed and right-handed shapes. They are mirror images, like your own hands. But when we look at life on Earth, from the bacteria in the soil, to the trees in the forest, to the cells in your body, we find only left-handed amino acids. Why? Why did nature choose a side? Perhaps it was a chance event in the early solar nebula. Perhaps the first successful chain just happened to be left-handed and it consumed all the resources, starving out the right-handed competition. It is a ghost in the machine, a fingerprint from the dawn of time that every living thing still carries today. What is happening here is profound. Consider the alphabet. With just 26 letters, you can write every book in every library, every poem, every law, every love letter. The letters themselves have no meaning, but arrange them in a specific order and you create Shakespeare, you create Einstein. Amino acids are the alphabet of life. There are hundreds of types, but life on Earth chose just 20 specific ones, the canonical 20. In those warm, drying pools of the Hadean Earth, these 20 letters were being shuffled, random combinations. Most were nonsense, static, useless. But purely by chance, some combinations began to do something new. They folded. They created shapes. They created function. This was no longer just chemistry. This was the prelude to biology. Matter was beginning to store information. Matter was beginning to remember. These primitive chains, these pre-proteins, were the ancestors of the machinery inside you right now. The hemoglobin that carries your oxygen, the insulin that regulates your sugar, the keratin in your fingernails, it all started here in the mud and the lightning. It is humbling to look back across the abyss of time, to realize that the difference between a rock and a human is not the atoms themselves. We are made of the same carbon, the same nitrogen, the same stardust as the barren asteroids drifting in the dark. The difference is the arrangement. The difference is the complexity. Look at your hand. Turn it over. Look at the veins beneath your skin. Feel the rhythm of your pulse. That blood flowing through you is a salty echo of the primordial ocean. The proteins building your cells are the direct descendants of those first fragile chains forged in the storm. You are not separate from this planet. You are not a visitor. You are the Earth that has learned to walk. You are the universe that has learned to think. The fires have finally died, leaving behind a silent, global ocean wrapping the planet. Earth is no longer a hellscape, but a water world waiting for its purpose. Yet beneath the waves, the silence is deafening. No fish, no plants, no breath. Deep below, hydrothermal vents pump heat and raw minerals into the dark abyss. The ingredients are present, drifting aimlessly in a vast primordial chemical soup. But the stage remains empty. The miracle of consciousness has not yet arrived. What single impossible moment turned dead matter into the very first living cell? Join us next time as we solve the universe's greatest mystery, the origin of life.